Okay, I did exercises 22 and 23 yesterday. Now I'm going to do 24. And 24 is quite a nice example because it's got a lot of stuff going on. So if you just read it, it sounds like someone's flinging information at your head and you don't quite know what's going on. Let's see, denote, oh goodness me, denote. What a big word. Let's see, denote the first octant arc of the curve in which paraboloid that thing and plane that other thing intersect. Already that's a bunch of information. Find the points on C which are closest to and farthest from the origin. And then find the minimum maximum distances from the origin to C. And you look at that and you think, I don't even know where to start. So where you start is you ask yourself, what am I trying to maximize or minimize? That's where you start. And you think, okay, the thing I'm trying to optimize is distance, because I'm trying to find closest and furthest. So that's the thing I'm trying to optimize. So far, paraboloid, plane, curves, they haven't actually even come into the story yet. The thing I'm trying to maximize or minimize is distance, and we know our distance formula. Our distance of a point with coordinates x, y, z from the origin is the square root of x squared plus y squared plus z squared. And that is the thing that we're trying to maximize or minimize. Okay? Question?
For these types of questions, we always have to, second, first thing.
Yeah. Yes. Yes. You always... no, sometimes... Well, in fact... Yeah, pretty much. Let's have a look at exercise 31. 31 is an exception to that. It says find the maximum and minima of this thing subject to that thing. And there it's perfectly clear. Usually it's not perfectly clear. You have to read it and you have to kind of take a deep breath and say, I can do this. What am I trying to maximize or minimize? That thing over there, okay, that's my f of x, y, whatever. And then what is the constraint? And then you have some constraint. Okay, so... that's over there, that distance formula, that's the thing we're trying to maximize or minimize. Now, if you read through these problems, it's not uncommon to maximize or minimize a distance. Let me show you a good trick. I am going to come up with a different function, which just for fun I'm going to call capital D. And it's actually just the stuff inside the square root. Because think about it for a second. If we're trying to maximize distance, we are simultaneously let me rephrase. If we find a point that maximizes distance, we are simultaneously finding a point that maximizes distance squared, or minimizes, whatever the optimum is that you're finding. If I work out the distance from me to everybody in this classroom, maximum would probably be, what's maximum? Probably you over there in the corner, in the woolly hat. Mr. Dupree. You're probably the furthest person from me. So if I were working out distance from me to everybody here, that would probably be maximum distance. But if I work out the square of all my distances to you, so I still solve for the same point. Because maximum distance, the point with maximum distance is the same point that has maximum distance squared. Does that make sense? So by finding the point that maximizes little d, I'm also finding the point that maximizes big D, and it's so much easier to maximize big D because it doesn't have a square root in it. So be my guest and maximize little d, but by maximizing big D, or minimizing, whatever the case is, big D, you are solving for the same point. And so therefore you're achieving the same solution, because what we're trying to find ultimately is the point. Okay, so it's a nice trick in these maximize, minimize distance problems to actually work with big D rather than with little d, because you'll achieve the same result, but easier, in an easier process. Okay, so that's the thing we're trying to maximize or minimize. What's the constraint? We actually have two constraints, because we're trying to solve for points, right? We're trying to solve for points in space. Which ones are furthest and closest to the origin? Well, what's constraining those points? Can they be anywhere? They can't be anywhere. They have to satisfy. They have to be on the curve of intersection of the paraboloid and the plane. In other words, they need to satisfy the plane equation, and they also need to satisfy the paraboloid equation. So I'm not actually going to solve for the curve of intersection. I'm just going to say the points that I'm looking for need to simultaneously satisfy both of my surface equations. So I have two constraints, And the one constraint is, okay, I could push the variables across in either direction. I just want to make sure that I do the same as in my notes. So look at that paraboloid equation, 2z equals 16 minus x squared minus y squared, and think about how your constraint formula needs to look. It needs to look like some or other function equals constant. So I'm going to shove all the variables over to the same side of the equal sign. X squared plus y squared plus 2z equals 16. And my points also need to satisfy the plane equation, which is in fact already constructed in the way we want. Those are my two constraints, which I'm calling G and H. Yes?
You don't care about orientation here with Z.
No, we don't. We're not dealing with oriented surfaces here, we're just interested in the curve of intersection. Okay, so the way I have interpreted the information in the question is possibly not the way you expected it to be interpreted. Because first of all, the information that's flung at you straight away is a paraboloid and a plane. And yet the very first thing I wrote down was not the paraboloid equation or the plane equation, it was the distance formula, because that's the thing I'm maximizing or minimizing. Also, if you read the question goes on, let's see, denote the the curve of intersection. But I haven't found my curve of intersection because I'm not actually interested in the curve. I'm interested in points that are constrained by having to be on the curve. And what defines the curve? It's the points that simultaneously satisfy both surface equations. So these Lagrange multiplier questions, sometimes you need to read them and stop and think about what exactly are you trying to maximize or minimize and what are the constraints, because you might end up interpreting the information in the question slightly different than what your sort of instinctive reaction was when you first saw it. Okay, alrighty then. Now that we have those equations, now we can jump into setting up our system of simultaneous equations that we need to solve and then solving them. Okay, yes, question?
Why would you keep them separate than you do three grads finding h bar equal and h 1?
Sorry, I'm not following you. Say again.
Why would you not do the curve of intersection?
Well, you can find the curve of intersection, but then you need to construct. I need a Cartesian expression that I can work out the grad of in order to use the Lagrange multiplier process. So there might be other ways of finding this information, of which points on the curve are closest to inference from the origin. But if I want to use the Lagrange multiplier process, I need my thing I'm trying to optimize and the constraints expressed in Cartesian form. So if I actually find my curve of intersection, that's interesting information, but it's not useful for Lagrange multipliers because it'll be a vector equation. It'll be R of t something or other. So there are undoubtedly other ways of solving for the same information. Okay, so there's my grad D. My grad G is 2x, 2y, 2. My grad H is 1, 1, 0, because there is no z in it. Okay, I'm now going to have two actual multipliers. Remember, lambda was my multiplier. I'm now going to have a lambda and a mu. I'm going to have that my grad D equals lambda grad G plus mu grad H. So 2x equals 2 lambda x plus mu. Oh, golly, why do we add them? No, there'll be a profound answer to that question that isn't immediately coming to me. Because why do we add them? Why don't we multiply them or divide them? Why are we adding them? I do not, in fact, have an immediate answer to that question, and I have to give you the rather cop-out answer because it works. But there must be a good answer to the question. Going out of the course on a low point. 2 lambda y plus mu, and then 2z equals 2 lambda plus 0 mu. Let me just write that there just for completeness. And then, of course, there are my actual constraints themselves, which I've now scrolled past. X squared plus y squared plus 2z equals 16. and x plus y equals 4, and I'm going to number these equations. This is my set, or my system rather, system is the correct word. This is my system of equations, system of equations that I now need to solve. 5 equations and 5 unknowns, where those unknowns are x, y, z, lambda and mu. Although, as I said yesterday, lambda and mu we're not actually really interested in. They're simply there to allow us to solve for x, y, and z. Okay, so now you need to solve that. How the heck are you going to solve for that? Well, there's an interesting effect going on in equations 1 and 2. Because we can see that those equations 1 and 2 are very similar. If I make x the subject, 2x minus 2 lambda x equals mu. In other words, x equals mu over 2 minus 2 lambda. And in the second one, if I make y the subject, I'm going to get y equals mu over 2 minus 2 lambda. Those are equal. That implies that x equals y. So that's a useful piece of information.
Could we get that by inspection, or isn't it equivalent? I mean, it seems quite obvious that there's...
You can do it by inspection. You can do it by inspection. So, an analogy that I find illustrative with Lagrange multipliers is it's almost like when you're solving these things and you're sitting there at a table at your desk and you've got a piece of paper in front of you and you're solving these things, it almost feels like someone's thrown a handful of marbles on the desk and you have to keep them from falling on the floor. And it's so easy for these solutions to fall on the floor and get lost. Because what I've just done there has lost a solution. What solution have I lost? Not lambda equals 0. Lambda equals 1. By doing what I just did, I have said lambda is not allowed to be 1. Because if lambda is 1, I've got division by 0. So I'm airily saying, oh, lambda is not allowed to be 1. But maybe lambda can be 1. We don't know yet. We can't close the door on any solutions. Or lambda equals 1. Well, no, that's not a right thing to say. Only if lambda is not equal to 1. Okay, let's put it that way rather. Because I don't know that lambda equals 1 is a legit solution, but maybe it is. Okay. All right, let me call this result 6, this x equals y. If I take result 6 and put it into equation number 5, x and y are equal and they add to 4, it must mean that x equals y equals 2. Lovely, that's a solution, but maybe it's not the only solution. Question at the back?
Now, it's obvious to see that lambda probably wants to be clear enough. If you're looking at it in the original form, how would you be able to see that?
Well, that's the whole thing. If you look at the original equations, there's no reason why lambda can't be 1. That's why we have to take it into consideration, which is what I'm just about to do. There's a question over there?
Then why can we still keep working with those equations? Because surely anything that we do using x equals y would eliminate.
It means x equals y is not compatible with lambda equals 1. But that means we've got one solution set. But now we need to look at the possibility of a different solution set where lambda is 1. If lambda is not 1, then x is certainly equal to y. But if, did I say that right? If lambda is not 1. If lambda is not 1, then those two little things that I've written there, at the those two things there with all the implication signs, everything I've written there is completely logically correct. But it's only logically correct in the world where lambda is not 1. So I've got one box of solutions, and in that box of solutions, lambda is not 1. X is certainly equal to y, which means they both are equal to 2. But I have another box of solutions where lambda equals 1, and now I need to pursue that. What if lambda equals 1? If lambda equals 1, then let's have a look. What do I have? If lambda equals 1, oh, look at that. If lambda equals 1, look at equation 3. Equation 3, which says 2z equals 2, which implies that z equals 1. Okay. If z equals 1, let me call that result 7. If I put result 7 into equation 4, I always number these things. Maybe you don't have to. But they get so... It's all these marbles trying to fall off the table. You've got to keep track of them. So I number everything strictly so I can pin it down on the page and so it doesn't run away. But that's just my own personal process. You don't have to do that. What you do have to do is get these problems right, whatever method you use. So that would give me x squared plus y squared plus 2 equals 16. In other words, x squared plus y squared equals 14. All right. Okay. So now... So I've got x squared plus y squared equals 14. But I've still got, let's have a look, x plus y. I'm going to use the x plus y equals 4. So let's have a look. What number have I got up to? 7. I'm going to call that 8. If you look at my Vuller solutions, you'll see I've numbered things slightly differently. So even though I'm doing the same sort of process, the numbering diverged from what will go up on Vuller a little while ago. And remember good old equation 5, x plus y equals 4. Here I have 2 simultaneous equations and 2 unknowns. Nice return to high school there. You can solve for x and y. X plus y equals 4, so x equals 4 minus y. Let me call that result 9. I'm going to put result 9 into result 8, which is x squared. X squared is 4 minus y squared plus y squared equals 14. So 16 minus 2y plus y squared equals 14. So,
Minus 8.
60 minus 8. Absolutely. Thank you. I remember the times by 2, but not the times by 4. Oh, my standard 6 maths teacher. Somewhere she felt a pain. Somebody squared a binomial incorrectly. That was Mrs. Immig. I still remember you, Mrs. Immig. 2y squared minus 8y. And you must remember, I was very good at maths in high school. I would like to think I was, otherwise I wouldn't have become a maths lecturer later. So generally my teachers were not that mean to me. So maths teachers I remember with great fondness. Not so much phys ed teachers. Those I do not remember with great fondness. 16, where am I? Minus 14, so that's 2. Let me divide through by 2. And that does not factorize nicely, so I'm going to have to use my root formula. Oh my goodness, when do you learn your root formula? Grade what? 9. Grade 9, sure. You were like this big. This is junior work and you're all gasping. Come on. B squared minus 4ac. 12 is 4 times 3, so you can pull the 4 out, and so this becomes 2 plus minus root 3. Phew! And x is 4 minus that. Four minus 2 plus root 3. 4 minus 2 minus root 3. It becomes 2 minus root 3, 2 plus root 3. Whew! So what is my set of solutions? In the case where lambda is not 1, my solution is x equals 2, y equals 2, z equals something. I'll work it out in a second. And the case where lambda does equal 1, then my solutions are x equals 2 minus root 3, y equals 2 plus root 3, z equals 1. Catch up with me, stylus.
Shouldn't we have something that has a 6 plus? Because it's plus or minus.
Give me a sec and I'll catch up with you. 6, sorry. What's that about a 6?
No, never mind.
Okay, all right, I won't mind. If x is 2 and y is 2, then z, how are we going to find z? We're going to find z from equation 4 probably. And equation 4 says x squared plus y squared plus 2z equals 16. So 4 plus 4 is 8. So it's 16 minus 8, which is 8. And then so z is 4. Okay. I got that from equation 4. Basically, I have x and y, so I can find out z by plugging it back in. Not a big deal. And that is my solution set. And see how, if I had blithely done that x equals that thing with the mu and the lambdas and y, and said, oh, look, they're the same, x must equal y, and I had missed the fact that lambda equals 1 was not compatible, I would have actually lost 2/3 of my answer. Because 2 of the 3 solutions came from the lambda equals 1 situation, which are both negated by that division that happened very early on in my solution process. Question?
Where did you get the x minus 1 minus y? What equation was that?
That was equation, let's go back to what I did here. It was early on. It was the one constraint, number 5. And then that thing over there I got from question.
So when we divide by a variable, so like you said, we divide by x, we're using x equals 0.
Yes.
So then we do it the same like this?
Yes.
Or then if you say a solution?
Yeah, that's right. So as soon as you do a division involving a variable, it means that you're kind of reaching a splitting of paths. And you're going down the path where that variable's not allowed to be whatever results in division by 0. And that's fine, that's totally fine, but you need to remember it. And when you finish, when you come to the end of that path, you need to come back to that fork in the road and go down the other path where that variable actually is equal to the thing that results in division by 0. And it means, obviously, you'll have to choose a different solution process in order to solve for your points. So it's fine to do that sort of thing as long as you know that you're doing it and you come back later and you say, well, what if? And sometimes you'll do something like you'll come back to the lambda equals 1 case and you'll realize, oh, it results in some sort of contradiction and actually lambda could never have been 1 all along and so it's all right. But sometimes you will, well, not in this particular example, but there are others where you could do that. You could come back to that fork in the road and go, oh, actually, that other path I was going to go down, for some or other reason, it's actually impossible. So the solutions that I found actually is the full set. But you do need to do that process of coming back to that fork in the road and saying, okay, what about this other option? Question at the back?
The reason we didn't take into consideration mu is because it didn't have any change in the answers.
Yeah, so mu in the end actually ended up playing no role in our thing. Although you'll notice that if you look at the solutions I'm putting up on Vula, I have actually solved for lambda and mu in each of these cases. And that's largely because when I was first drawing up, so you'll see how many there are. I mean, Lagrange multipliers, there are how many of them? There's 2 pages of them. And I got them from old tests and exams. These are popular questions. And I put them roughly in order of difficulty, although I chose the 3 I've chosen as a range, but then roughly after that they're in order of difficulty. And when I was drawing up the solutions, I kept finding myself losing solutions and then coming back and going, oh goodness, I didn't check out the lambda equals 1 option and things like that. So I solved for lambda and mu as well in all of these solutions, basically as a way of forcing myself to be sure that I had considered all the options. But fundamentally, we're not interested in lambda and mu. Question?
Would you mind just explaining how we got those in solutions at actual points?
So in fact, let me actually draw it as almost as a path. So there's the path where lambda is not equal to 1, and where did it take us? It took us to x equals y. And then there was the path of maybe lambda equals 1, and it took us to z equals 1. Those were the destinations of those two. No, I didn't want a page jump. Man, what a wasted page. We don't need it. Now I'm going to have to figure out how to delete the page, which there is a way to do, but it's actually a bit involved. X equals y. So those are the little ends of the roads that we got to. And then x equals y took us to z equals 4, and z equals 1 took us to the x, y equals plus, that 2 plus minus root 3. Y equals 2 plus minus root 3, and x equals 2 minus plus root 3. So I don't know whether that helps. So we chose a solution process that took us to x equals y, but we kind of flagged the fact that lambda couldn't equal 1. And we have to come back later to the fork in the road and follow the lambda equals 1 road. Okay, cool. That gave us x equals y. X equals y gave us that x equals y equals 2, which then gave us that z equals 4. Okay, then we come back to the fork in the road and we say, well, what if lambda equals 1? So we plug lambda equals 1 in and we go, oh, the thing that gives us is that z equals 1. Yay! There's our piece of information. We're going to take that z equals 1 piece of information and use it to allow us to solve for x and y. But I think that's enough of me talking. You need to go. It's 15 minutes left of the last lecture of the semester. Why don't you give it a go? Try numbers 25 and 26. Yeah. Okay, I'm being reminded that I didn't quite finish. While I found 3 points, I didn't actually solve for their distances. So we can actually solve for their distances. So D, the big D, which of course is the square of the distance, big D at 2, 2, 4, if you plug it into your distance formula, gives you 15. Big D at these other 2 points, I think gives you the same distance. Oh, no, those are the 15. 2 to 4 is 24. I'll come back and fix that. That's 1D at 2 plus root 3. Sorry, I'm being a bit scruffy here. Shouldn't be that, and that's wrong, and that's 15, and that's 15, and that's 24. This is the maximum distance. The maximum distance is root 24, and both of those points give me a minimum distance of root 15. Okay, and you can trust that the smallest will be minimum and the biggest will be maximum. The other 2 problems we did, I think, only had a single optimum, and so we needed to be a bit creative. As soon as you have multiple optima, smallest is true smallest, and largest is the true largest, is what you're looking for. Okay, I'll pause again.